Hey, good morning, everyone. Welcome to Monday, our CE design class. Thank you for being here today. First of all, can you guys hear me? If you do, give me a thumbs up.
Yeah, we can.
All right, good deal, good deal. Thank you so much for accommodating. Actually, I'm traveling right now and things are going well. Hopefully we'll get everything cleared out. But now let's go back to our CE design class. And today we're going to continue our route to discuss about the flange, which is a T-shaped beam design. And we'll go through some of the scenarios again and go through the example, hopefully at a time. Now, a few updates. I mentioned that I will do a recorded video lecture. After checking, I realized that we are actually on schedule, so I don't think we're behind. Instead, I'm adding one more section next Tuesday, and that is, let me check the time right now. That is Tuesday on the 15th, say in the afternoon session, like say 2 or 3 o'clock. And it's office hour. Feel free to come, or if you're busy, you can watch recorded videos. So that I think will help more instead of doing the recorded video. Okay, and I will upload the grades today, and you can check your homework today and make sure that you have any question you can ask me next Tuesday. If you haven't, please go through the exam number 1, sample exam number 1. I uploaded to Canvas, and we can talk about it next Tuesday as well. Okay, as well. All right, so first of all, where we are, right? What we have learned so far. So last time we were in the T-beam, right? So this is the T-beam, right? So we have a section. We're trying to find out what is the effective beam width. What is the effective beam width? So we know that the B effective has 2 parts. One is the web and the other is the flange, right? So we need to determine how much is the flange width we have here. To find out that, all we need to do right now is to go to the code and find these equations, right? So BF equal to least of the 3, and BE equal to this bunch. And for L-shaped BF, it's a little bit different, right? So a little bit shorter. So that's how we determine BF based on the code, And here's an example, right? And I put it as a quiz right here, as you ask you to find out the B effective for all the different scenarios. So as you can see that you have different sections, right? The most important thing we have covered is that when you have a different span length, adjacent span length, that is on the T-beam on the left side of it has one span length, for example, in this case, 12 feet. And on the right-hand side of it, have a different span length that is 13 feet. We need to find the span length, which is SW. In this case, you would do the average and find out the SW, right? So the average right now is SW. Between them two is, where is it at? Let me see, Okay, SW is 12 plus 13 divided by 2, right? 12 plus 13 divided by 2 right here. Okay, so don't forget to take the average when you have a different span length in the adjacent span, Okay, so after you find the B effective, you basically have your section now, right? You have your section, which looks quite a nice T section right here. You have a B effective, that is BW plus 2BF, and have a BW here as a web. And now when you calculate all the section stress distribution, you realize that you might have a situation that for the stress distribution in the flange and in the web, they're slightly different. When I say slightly, they're actually quite different, right? So the web still follow the Whitney stress block, 0.85 prime C, BW, and A, which is the effective beam width, effective compressive zone size. And for the flange, you actually have to take the whole HF as the compressive zone, Now, given that HF is the flange height. Okay, so that's what we realized. And then we went on and say, okay, look, when we have this section, we now have total compression force from the concrete can be split into the compression from the web, compression from the flange, then went down for calculations, right? And then we suddenly realized that the total compression, that is compression from the web, plus the compression from the flange has to add up to the total tension, that is ASFY. And then we immediately realize that we have to split the tensile reinforcement in 2 components. That is AS would have to equal to AS1 and AS2. So this way we can have the total reinforcement split between the balance force for the flange and the balancing force for the web, right? So that's where we're at last time, So in the short summary here, what we have learned is that for T-beam design, the stress distribution can be quite challenging. The stress distribution can be quite challenging. So when you try to design it, right, the most important question still remains, that is, what is A? What is effective compressive zone size A? Effective compressive zone size A. So this has been the eternal theme for the flexure design of concrete beams, right? What is the effective compressive zone A? So if we know A, natural A, we know that A equal to beta 1C. So C equal to A divided by beta 1. And mind you that beta 1 is dependent on the concrete compressive strength, and then we can find out the moment, right? So that's the whole story is all about. But for T section, apparently the old scheme of using tension equal to compression and divided by the whole windy stress block thing does not work anymore. Right? So in this case, I want us to start fresh. So here we have to say that now for T-beam design, we will have to design it for two different scenarios. Okay, so this is slightly different from the rectangular section, So scenario 1, that is A smaller or equal to HF. Okay, so when the compressive zone, effective compressive zone is smaller than the flange height, what happens, right? So let me draw the T section out again, right? So let's you have a mental image. of what we're dealing with here, right? So this is a nice T section, and the BE is right here. Don't forget, this is the BE effective. All right, and the BW is right here. Okay, so A is the effective zone size, right? A is effective zone size. So that means A is right here, because A is smaller than HF, where HF is the flange height. Okay, and what does it mean? It means that I look at the section and I realize that, okay, I just have a effective compressive zone within the flange. So I start looking at the section, right? I say that, okay, in terms of concrete, I can carry compression, but I cannot carry what? Okay, I'm gonna pick my next victim here. Don't think you can escape just because we're online. Let me see here, who's my next victim? Let me see here, Alex Durbin, are you there?
Yeah, I'm here.
Hey, how are you doing, man?
Doing great.
Yeah, all right, good to hear. So quick question here. So if I say that concrete is good for compression, concrete is not good for what?
It's not good for tension.
So that's right. When we have a singly reinforced rectangular beam, remember what we said about the bottom portion of the neutral axis. What did we say about it?
The bottom portion will be in tension.
So do we consider any tensile strength from it, or we don't?
We don't,
right? That's correct. And instead, what we do, we use the steel or tension from the steel. Is that right?
Yeah.
All righty. Thank you. That's the right answer, right? So from that, we know that if I'm looking at a rectangular section and I have my compressive zone, right? So that is right here. And although this is not neutral axis, but that is the effective compressive zone. But essentially, what we're trying to say is that the black shaded area does not contribute anything at all. Is that right? Because they do not contribute to tension. So in essence, I can say now, if my A is smaller than HF, essentially, I have a T section, but it acts just like a rectangular section. All right, because underneath the compression doesn't matter anymore for concrete, so it's the same. It's the same. So with this, I say, well, if you're so lucky, you say that when A is smaller than or equal to HF, you can treat the T section as a rectangular section. All right, you can treat a T as a rectangular section. Okay, so if that's the case, things are much easier. Things are much easier because if I can treat that, it's just an old-fashioned rectangular section that becomes old problem, right? Old problem that we all know how to solve. And here is my BE. Don't forget, here is my BE, and then my stress distribution looks just like this. Well, actually, that's my strain distribution, looks just like this. So epsilon Cu, compressive strain of concrete equals 0.03, and the tensile strain right here for the steel is right here. All right, and then you have the depths, as we talked about before. And you can compute the total compression. And let me write down here. So you have the, we need stress block again. Let me just map out a little bit better. So this is extension right here. So this is my A. And my total compression force CC will be here. And this is half A. And I have the distance between my tension force T equal to AS Fy. And the distance between the compression and the tension is the DOR, right? So this recovers our rectangular section solution. So Mn would equal to tension multiplied distance. And for that distance, Alexander, are you there?
Yep.
Hey, how are you doing, man?
I'm doing okay.
Good to hear. So Mn equal to T, can you help me finish the equation here, which is ds or dt?
DS.
Yes, right, minus?
Oh, A divided by 2.
A divided by 2. There you go. Thank you so much. That's it, right? That is the moment that, as before, total compression got equal to tension, so CC equal to T, and 0.85 F prime C BE. Okay, folks, be careful. BE, okay, multiply A, and that equal to ASFY. So you can find A and have to make sure that that is smaller than HF. All right, so pretty much that's what we do when you have scenario number 1. That is A is smaller than or equal to HF. So you treat it as rectangular section, you find A, and you proceed as we did before, right? So no hustle, right? Everything just before. But here comes the bomb, right? Here comes the difficult part. What if I am in scenario number 2? That is A, oops, sorry, mix up here. So comma, colon, A has to be greater than HF. When A is greater than HF, right? I'm looking at my section again. I realize that when A is greater than HF, I'm looking at T section right here. My T section is right here. And I say, my A is somewhere here. And this is my A. So the total shaded area now include the flange as well. And this is HF. So I have an extra part extending in the web only. It's called A minus HF. A minus HF. Okay. So when this happened, remember what we said before in last lecture? So we said that this equivalent to a separated stress, right? So you have the block, you have the rectangular block. I'm gonna just dash out the web section, right? Dash out the web section. You have the block. This is the wing. So here you have all the compression. So remember all the shaded air compression, and this is 0.85 F prime C. And you have now, which is HF and BF. And this is another one, 0.85 F prime C, HF, BF, right? So now the compression from the flange, is total CCF equal to 2 times 0.85 F prime C HF multiplied by BF. Okay, and then plus, right? Plus, and now this is the web, right? So let me dashed out the flange and have this web thing here dashed out, but the web here stick out like this, and this is BW, not BE anymore, okay, BW, okay? And now shaded area right here, and this is my A. Okay, so my compression force from the web, CCW, would equal to what? CCW would equal to 0.85 F prime C A B W. All right, so from get-go, I can now say AS1, that is the tension force from the flange, should equal to AS1 from flange should equal to CCF. So that is 2 times 0.85 F prime C HF BF. Or if I just want to use web, and you see this a lot, that is 0.85 F prime C HF. Here, BE minus BW. It's the same thing, right? BE is the total width of the flange anyway, and minus the BW give me the flange, right? So you can use 2 times BF or BE minus BW. Both are okay. Both are okay. Matter of fact, you see them a lot. You see them a lot, right? So this is what the first part is. So you can actually say that AS1 equal to this bunch, 0.85 F prime C. Sorry, got one folk join us. And then HF, and this is BE minus BW divided by Fy. And then the moment caused by the flange, let me call it Mn1, okay? You can call it Mf as well, okay? They're the same thing, but usually in this context, I just call it Mn1, okay? Just to simplify things. So Mn1 would equal to ASY, AS1 Fy, that is the total tension force, and the lever arm is ds minus. Now, here's the question. What is distance between the reinforcement and to the total compression force of the flange, right? So this is HF minus 2. So here, this is HF divided by 2, divided by 2, okay? So that is the moment caused by the flange. Now, correspondingly for the web section, things are a little bit easier. Now, AS2 Fy equal to 0.85 F prime C A BW. So AS2 equal to 0.85 F prime C A BW divided by Fy. And now the moment Mn2, or again, you can call it Mn web, doesn't matter what you call it, it's the same thing here. And that equal to AS2 Fy, and the lever arm here is ds minus half A. Okay, so you find these two moments and you say now the nominal flexure capacity or moment for the entire section is equal to Mn1 plus Mn2. Okay, all right, so is this clear? Any question about it? Folks, any question about it? Everybody's good with this? All right, so this is not too bad, right? So now with this, I say, okay, if this is the case, I now say phi Mn has to be greater than or equal to Mu. And I call it analysis is over, okay? Analysis is over. All right, so this is analysis for the T-beam section, okay? This analysis for the T-beam section. So I am going to fast forward a little bit because you know already how to analyze a singly reinforced section, all right? And now we also went over the design for singly reinforced section. So here I'm going to combine the analysis and design for T-beam design together, okay? Because you know the scenario. And I'm gonna go through that with one example, okay? I'm gonna go through that with one example. We have follow-up example, but today, let's just go through one example for now, okay? So now with this, I say, all right, this is just a series, right? So all I have to do is divide by 2 scenarios to see if it's scenario 1, scenario 2, and then do the analysis accordingly. Then add up, make sure that the capacity is bigger than the required. I'm done, right? So here is one simple example to show that. So example, okay, example on T-beam design. So T-beam design. Okay, and again, folks, for T-beam, you can quote me on this. In this class, we're only testing you on the known section size design, right? Remember, for the design, we have known section and we have unknown section, right? For this case, T-beam, we always have a known section. We always have a known section, okay? And give you some parameters. F prime C is 3 KSI concrete, very rare, very rare, okay? Immediately, you know that beta 1 for 3 KSI concrete is a little bit different, okay? You think about it, it's not 0.85. Just remind, it's not 0.85, okay? And it's grade 60, so it implies that yield strength of the bar 60 KSI. All right, and we're going to ask you design for the reinforcement only. Design for reinforcement only. What is the total reinforcement area? And also tell you that it has to have a Feynman greater than equal to mu, and that is 533 kip/foot. Okay, so factor moment is given. Factor moment is given, and you wanted the geometry, right? So the geometry looks just like this. It's nice T-beam. Nice T-beam, and usually I will ask you guys to find out what is the effective flange width and everything. But for this case, I'm just going to tell you that BE effective flange width is going to equal to 47 inch, and BW for this thing equal to 11 inch. The height of the flange is equal to a 3 inch. Okay. And then the depths of it, I even tell you the depths, right? The depths of it, AS right here, and that is equal to DS, 20 inch. All right. The total height, of course, is 23 inch. And now you have a little bit interesting thing is this part, you don't see this in rectangular section, but might as well just tell you that this part is actually just 20 inch. Okay, 20 inch. All right. So now for this design, what we're going to do, right? What we're going to do is, first of all, design it, right? So design, step number 1, right? Step number 1, asking us, right? How much of total reinforcement needed? How much of total reinforcement needed? Okay, so in this scenario, right? In this case, we're going to go by this. We're going to assume scenario number 1 first. We're going to assume scenario number 1 first. If scenario 1 doesn't cover it, and we're going to go back to scenario 2. Okay. If scenario 1 doesn't cover it, we're going to go by scenario number 2. Okay. So in this case, we say assume scenario 1 first. Okay. Assume scenario 1. So what is scenario 1 anyway? The compressive zone A is smaller than HF, smaller or equal to HF, smaller than or equal to HF. Okay, so for this, I say, all right, step number 1, let me estimate the total reinforcement, just like what we do for a singly reinforced rectangular section, right? Because remember, the implication behind this is that treat the T as rectangular section. Okay, so to estimate AS required, and you again assume several things, right? But AS required by the singly reinforced, right? Singly reinforced rectangular section, okay? I'm just simplify it. So assume that, and this AS required equal to mu divided by phi and Fy, and this is 0.9 ds. Remember, when we don't know the effective compressive zone A, and we're going to use this, right? But different here, I just want to label it out, okay? It's not 0.9 anymore for T, okay? For T-beam, okay? For T-beam, because typically the depth's a little bit different, we're going to use 0.95 ds, okay? This is very important. Change, okay, due to a T-beam shape, change due to a T-beam shape. That is to say that now AS required for this case would equal to, well, let me just move this to the next page. So later when I convert, you will still see this, okay? AS required, that equal to, has to be mu factor moment divided by phi and 0.9, which we always assume, and then Fy, and then 0.95 ds. Okay, so that is how much require reinforcement, how much reinforcement required. So bring the number in, AS required, ES required equal to mu, that is 533 kip/foot. Convert everything back to inches, right? 12 inch per foot, and divided by 0.9, 60 KSI multiplied by 0.95, and ds equal to a 20 inch. So AS required, you punch the number in, and I got, and to save your time, 6.24 inch squared. Okay, That is how much reinforcement I needed. Okay, and given that, I assume scenario number one, remember, assume scenario, so I need to check A to ensure that it is smaller than HF, right? So now I first to do is estimate the required reinforcement. Remember in the big old design book, we need to check A, right? So in the design, we say check A. Okay, so now A equal to AS required multiplied by FY divided by a 0.85 at prime C and B. And now B, remember, we have a teak section, but now if the compressive zone is smaller than HF, you treat it as a rectangular section. And when you treat it as a rectangular section, this fellow right here is BE, that is BW plus 2BF. Don't forget, right? So this is BE right here, okay? This is BE right here. All right, so with that, let's bring the number in. A equal to 6.24 inch squared and multiply Fy 60 KSI and divided by a 0.85 and multiply 3 KSI concrete, lower strength concrete, and multiply 47 inch. Okay, so now with this, I say A, let's save you the time again, 3.12 inch, and that is inch is actually unfortunately bigger than HF, equal to 3 inch. Bigger than that, all right? What does it mean? It means that it is not scenario number one, right? So cannot be designed as scenario number one, right? Cannot be designed as one. So meaning has been denied as a rectangular section. Cannot do rectangular section, right? Cannot be rectangular section. So we go back to scenario number two, right? So we go back to scenario number two. So step two, assume scenario number two, right? So what is scenario number two? You know that we have the split, and put a little bit drawing here. We have to split the compression into the flange. Okay, I found this very helpful. Okay, you can try it yourself to see if that actually helps. But this is what I usually do, that to split between the web and the flange. Okay, to split. All right, so how do we split? Now 2.1 for scenario number two, okay? For the flange, first thing we do is that we have to say that the flange reinforcement AS2 Fy equal to 0.85 F prime C, here BE minus BW, remember? BE minus BW, and then don't forget our friend HF, okay? So now from there, I say AS2 would equal to 0.85 F prime C BE minus BW HF divided by a Fy. So now I left with AS2, bring the number in, equal to 0.85, 3 KSI concrete, and then BE 47 inch minus BW 11 inch multiplied by 3 inch of HF divided by 60 KSI. And I want to save your time again. So AS2 would equal to 4.59 inch squared. All right, 4.59 inch squared. Okay, so that is the flange. That is flange. Okay, now you notice that I've switched one or two quite often. Okay, so apologize. Let me go back to the original designation. Okay, so this is AS1. Sorry about that. AS1. Okay, AS1. So let me just label here 1 flange, 2 web. Okay. So AS1 is area for flange, AS2 is for the web. Okay. So that is 4.59 inch squared. Okay, apologize. Often happens, unfortunately. So 2.2, next step. Right, step 2.2, right? So for the flange, again, I have this much of area, right? I need to calculate the moment. So MNF, which is MN flange. So Why I always use 2, mn1 equal to 4.59 inch squared. That is this reinforcement area multiplied Fy 60 KSI. And then multiply by the lever arm, right? That is ds 20 inch minus HF divided by 2, so 3 inch divided by 2, okay? And then mn1 would equal to 424.6 kip foot. Okay, all right. So that is what we're doing with the flange, right? So 2.3. How about the web, right? How about the web? So now this is what we're doing. For the flange, we know that, okay? And pay attention here. For the flange, we know that the total compressive zone is within the flange, right? So that means I know HF to begin with, right? I know this fellow, I know everything I just went through to calculate the moment. Okay, I don't have to determine anything. But for the web, what the problem is, I actually don't know A. Is that right? I don't know A for the web, right? So in this scenario, right, we have to say that to determine, we have to determine A. For the web, right? We need to determine the compressive zone for the web. We need to know how much moment that has been attributed or coming from the web. So we need to know mn2, right? How do we know mn2? Now we have a requirement that is phi mn equal to phi mn1 plus phi mn2 has to be greater than or equal to mu. So in this case, phi mn2 would equal to or greater than mu minus phi mn1, or mn2, that is the web moment, has to be greater than or equal to mu divided by phi minus mn from the flange mn1. All right. All right. So now I know this, right? I can start doing the calculation and actually find out this is equal to mu's 533 kip foot. And don't forget, we assume the stress reduction factor phi equal to 0.9. So this is 0.9. mn1 is 424, this value right here, 424.6 kip foot. So now you end up with mn2 has to be greater than or equal to 159 kip foot, and this fellow divided by 0.9. Okay, now I really don't have the number mapped out. Anybody can help me out? Can I get a number on this? 150.9 divided by 0.9. I'm gonna wait for a few minutes. When you pull out your calculator, I'm gonna start calling names just so you can help me out. Let me see who's on my victim list. Who's on my victim list? Let me just pick a random person. Okay, whoever come out. Paul. Are you there?
Yes, sir.
Hey, how are you doing, man?
I'm doing all right. How are you?
Not too bad, except a little bit long distance here. But anyway, so can you help me out here? mn2 equal to 150.9 divided by 0.9. What you got here?
I have 167.67.
Great. That's seems a reasonable number. All right. Anybody get different? Going once. Anybody get different? Any different? Going twice. Any difference? Going third time. So, right. So we have 167.67 kip foot. Okay. Now with that, I say, okay, this is how much moment the web need. All right. The web need to have this much moment. Now with that, I say, okay, now I can determine A. I can determine A. But to determine A before that, I need to determine AS2. How much reinforcement needed for the web? So this becomes easy job, right? Because now I go back and look my sheet, and this is just the web. Remember, this is just the web. So I dash out the flange. This is my web. So I treat the web as a single reinforced rectangular section. So mn2, right? So mn2 equal to AS2 Fy and ds minus half A, right? Minus half A. Now, this is getting interesting, okay? Remember what we said for the flange, that is 0.95, but for the web, this is 0.9 ds, okay? I know this is annoying, but they are actually different. They're actually different because the web is a bit different from the flange, And if you take advanced concrete class later, I'll explain to you why, but for now, we can just bear with it and take 0.9 ds, right? So Mn2 equal to AS2 Fy multiplied by 0.9 ds. So AS2 has to equal to 100, well, let me just map out here. Mn2 divided by Fy, 0.9 ds. You bring the number in, 167.67, kept foot, convert everything by inch, 12 inch per foot, and then divided by 60 ksi, and 0.9, and ds is 20 inch. All right, and with that, I say AS2 turns out to be 1.9 inch squared. 1.9 inch squared. Okay, all right, so that is how much I have. That is how much I have for the web. So with this much of reinforcement area, I say, okay, now I want to determine my effective compressive zone A, final A. What is my A, final A, right? So A now has to go by the singular reinforced rectangular section again, right? So A would equal to AS2 Fy divided by A 0.85 F prime C, and B what? Now I'm going to choose my next victim here. I have A and P. Let me try a B. Blader, Mr. Elder, Blake, Elder, I'm sorry, Blake. Are you there?
Yeah.
Hey,
Yep,
how are you doing, man? Doing okay?
doing good.
All righty, good deal. So quick question here for you, sir. A equal to AS2 Fy divided by 0.85 prime C. I need the width. Now, will it be W or BE?
BW, right?
BW, that's right. Thank you so much. That's the right answer, right? So be careful, folks. We are dealing with, don't forget, right? We are dealing with the web right here, okay? We are dealing with the web right here, right? So you're going to use the BW. You're going to use the BW, okay? So that is the BW. Now, rest of it easy, right? Bring the number in. That is 1.9 inch squared and 60 ksi and divided by 0.85. 3 ksi concrete and a prime C, 3 ks BW, 11 inch. So I have this number out here is 4 inch. So A equal to 4 inch. And now let me call up a lady for help. Callie, Miss Hall, are you there?
Hello.
Hey, how are you doing, madam?
I'm good, thank you.
All right, good to hear that. So now, quick question for you, Callie. So A is equal to 4 inch, all right? And we assume, let me remind you, we assume scenario number 2. So are we good? Are we good? Is this scenario number 2?
1 second.
Yes, let's go back to take a look at the scenario number 2, right? What is the criterion for scenario number 2? I mean, how do we know it is scenario 1 or scenario number 2?
We need A to be bigger than HF.
That's right. So the compressive zone has to be bigger than the height of the flange. 100% perfect. Thank you, Callie. So we now know that A equal to 4 inch. So we simply compare with the HF, and that is 3 inch. So we say, good. Okay, it is scenario 2. Yippee! Everything's fine. Fantastic, right? So that is working along with our assumption very well. So now with this case, we'll say, all right, good deal. So 2.6, with everything said and done, I now have to say that the total required reinforcement, be careful folks, okay? The total required reinforcement would equal to AS1 plus AS2. So that is 4.59 inch squared. Where that 4.59 coming from? Go back to see, where is it? Right here, okay? Right here, okay? That is the estimated reinforcement for the flange. And added on the reinforcement needed for the web, 1.9 inch squared, right? 0.9 inch squared. So I have a total area of 6.6 inch squared. Perfect. Okay. All right. So 6.6 inch square, right? That's quite a bit. That's quite a bit, right? So if I say this is 6.6 inch squared, I need to put rebars here, right? So now I have a job to do that is 3 step. Well, don't have to put step here. Just say number 3, step number 3. I need to select the bars. Okay. All right, I'm gonna pick my next victim here. I need some help selecting bars. Drew, Mr. Lidditch, you there? Drew, are you there? Your mic working? No? Are you there? All right, Drew is not available. Seems like, okay, find the next victim here. Jacob, Shantz. Jacob,
Oh, yeah, I'm here.
hey, how are you doing, man?
I'm doing good. How are you?
Not too bad, not too bad. So I know my total required reinforcement is 6.6 inch squared. If I say I want to use number 9 bars, and first of all, what is cross-section area for number 9 bar? One number 9 bar,
It's 1 inch squared.
right? That is 1 inch squares. So if I say that I want to have a nice arrangement, right? So nice arrangement meaning I don't want to have single bars, right? I want to have perfect 2 rows or 2 columns of bars. So how many number 9 bars would you pick for me, sir?
You would need at least 7. So I guess if you want to make it asymmetrical, you go 8.
That's right. So I
Number
want
9 bars.
symmetric. Yes, perfect. Thank you very much. I want to make it symmetric, so easier for me to construct. I will select 8 number 9 bars. Wonderful. All right, 8 number 9 bars. So that is the good answer. So I have now number 9 bars, 8 of them. 8 of them. Okay. Now to put number 9 bars into the section, it's a little bit challenging, but still I can do that, right? I can do that. So I'm just going to put a drawing down here, and I say that look, this is BE, a 47 inch of total width. Excuse me, HF equal to 3 inch of a flange height, and the DS that is given, and no if, no buts, everything is said and done. It is 20 inch. I have to comply. Okay, I have to comply. Okay, although that may not be possible, but never mind, right? Let's just play along, say that I find a way to maintain everything within 20 inch, right? And now I have my beam width BW here equal to 11 inch. Okay, now what we have here? What we have here is now turn design into analysis. So this becomes old-fashioned of find at VMN and to make sure that it's greater than or equal to MU. Okay. All right. So that is what we're gonna do for Wednesday. That is what we're gonna do for Wednesday. Okay. Now, before I let you go, this actually will be our quiz number 2. Okay. So number 3. Okay. So quiz number 3. So we're just gonna label out here quiz number 3. And this is the quiz, okay? If you have a section, okay? If you have a section, all right? And the section is given B is 47 inch, flange is 3 inch, DS 20 inch, web is 11 inch, and knowing that F prime C is 3 KSI concrete, and yield strength of steel is grade 60, and I have 8 number 9 bars, 8 number 9 bars, and I need your help to find phi MN. And I need you to check if VMN is greater or equal to MU, that is 533 kip/foot. Okay, so this is quiz number 3. Quiz number 3. All right. Okay, so I will upload quiz number 3, and we will see you on Wednesday. All right. If you have any questions about homework, I know a few of you do have questions. Please stay behind, and we can discuss about them. Okay. All right. Thank you so much. See you later.